Okay, so what are we going to do in this course or the lectures or whatever it is, 7, 8, 10, I have no idea. But what are we going to see is how to prove lower bounds, okay? And when I say how to prove lower bounds, I'll explain what I mean by how to prove lower bounds. This is an important skill to have, irrespective of whether you work in any algorithm complexity, track A, track B, track D or E, it does not matter. And what is the current mantra is that if you have a box here, I will define what this box will, implies another box, and we'll try to understand what these two boxes are, okay? So what these boxes will mean, so first box is, this is what we try to do, surprisingly fast algorithm for your favorite problem. We'll quantify what this means. It implies, okay, some, what should it imply? Some known, or the best way to say, unexpected breakthroughs in theoretical computer science, okay? So this is what the whole idea of this lecture is how to quantify what do we mean by what is surprising fast algorithm means, and what does it imply to have an unexpected breakthrough in computer science, okay? Now, so first half an hour or so we'll try to understand what do we mean by surprisingly fast algorithm for your favorite problem, right? Now, surprisingly in what sense, and what do we mean by unexpected breakthrough in computer science, okay? So now let's start with some interesting, important, say, problems in P. Have you heard of this problem? Longest common sequence, LCS, right? What is input? Input is two string over some fixed alphabet, say binary, okay? So alphabet is fixed. Input is two strings x and y by over some alphabet, and what is an output? Longest common subsequence. Someone has to take lecture notes. Find it. This is part of our APC course, okay? It's just that I on purpose, but someone has to take a lecture notes. Okay, I need this. Okay. Okay. So for example, let's look at one example which I had. What it means for the problem, for example. Okay. Okay. So for example, I mean, if you have a two string, for example, so what does it mean to longest common subsequence? So let's see an example. So you have a string S and you have a string T, right? Say, or X or Y, it doesn't matter. X, let's stick to X and Y. And suppose we had C, D, D, C, A, B, B, A, B, C, B, A, right? And now I have another string A, D, B, D, B, B, C, A, D, B, C, A, B, A, C, D, D, right? Suppose I have this string, two strings and I'm looking for a longest common subsequence. So for example, the longest common sequence could be, for example, let's look at here D, and then we can have B, B, A, B, C, okay? And let's find out where this can be. So here is our DB here, and then we need B, B, another B. So let's, it doesn't matter, I can take any of these. So I just decided to pick this B, right? And then what we need? No, BB need, we need BA. I take BA here, but then am I stuck? Then I'm stuck, right? So basically I should take this B, then that A, this B and this C, right? So this is the longest common sequence between them, okay? Now if you have learned a high school algorithm or in a, you can do this in order n square time using normal dynamic programming, just keeping a coordinate, what is the longest common sequence between I and J, between M, I, J, and keep increasing, check in your CLRS book, you will find it. But
both X and Y have length n.
It doesn't matter. Suppose they have the same length, okay? Both have the same length, okay? Then we can do it in order n square time, okay? And there was a very nice development by Mezig and Peterson in 1980s, which basically said that, well, I don't know how to do it better, but probably I can do it in order n square divided by log square n, okay? So this is one problem which we are interested in. And what is the biggest open problem currently in this area is, can we do this in order n polylog n, okay? I'll come to this, okay? Not probably, he gave an algorithm with this, right? He gave, and this is what is open, okay? Now let's look at the another problem which is of interest, is what is called edit distance, okay? What do I mean by edit distance? Again, input is two strings xy, say of length n, okay? And your output is, what is your output? Your output is minimum number of edits, minimum number of insertions, deletion, insertion, deletion, substitution to transform x to y, right? So you are given two strings of length n, say x and y, and what are you allowed to do? You are allowed to insert, substitute and delete, and you want to transform x to y. This is what is basically edit distance problem is, okay? I am not going to give you an example, but fine. Again, this can be done in order n square time, do a normal dynamic programming algorithm. This is a classic dynamic programming algorithm, you can do this. And again, these people, Mesick, in the same paper actually, in 80, actually he gave an algorithm with running time n square log square n, okay? Okay, same question, we don't know, it's open, okay? Now let's look at threesome. What is threesome? What is an input? What is an input? You are given n integers, okay? And question is, does there exist three of them that sum to 0? n integers. So there are positive, negative, everything. And does there exist 3 of them that sums to 0, right? This also has order n square time algorithm. Can someone tell me what is this order n square time algorithm?
What you do is, okay, so
If you know, let's find that there are lots of younger people who have just started to do algorithm course. Does anybody know? Okay, we'll come back to that in a minute. Think about it. Okay. Fourth, APSP, all pair shortest path. So what is the input? Suppose you are given a graph G on n vertices and say roughly some big O of n square edges. Okay, this is what is given to you. And what do you need to output? What do you need to output? A matrix, or compute the distance between every pair of vertices. Okay. Now, what is the best known algorithm for this problem? Right? What is the best known algorithm for this problem? Huh? Everybody was very jumping for this. What is the best known algorithm for this problem? Do you know an algorithm for this problem? Everybody? So how much time does that algorithm take? Which algorithm is that? Okay. So, or even I think Dijkstra's, you can get an order NQ algorithm. Okay, this is the, and I think the best known algorithm for this currently is by I think Williams. I will check and tell you how much it is. I think it is some NQ 2 to the power big O of square root log n or something. But that's not important. Okay, so
the algorithms also has some circuit-based algorithms.
yes.
Oh, that is what that is.
Okay, fine.
Why is the requirement necessary?
What?
The dense, sparse.
Much better. Okay. Now let's write some more problems before we go. Get out of this world. Okay. Another problem which I would like to mention is 1, 2, 3, 4, 5. Let's put it here. Diameter. Input is G. Output the diameter of a graph of G. And what is diameter? It is max. So look at any pair of vertices, right? Look at the shortest distance between them, right? So you store all of them and you take the maximum of them, right? So it is maximum shortest distance between any pair of vertices. Okay, how much time does it take to get diameter of a graph?
Trivial algorithm will you have to compute for every pair and
Fine, but is that the only way to compute diameter? Can you compute diameter slightly faster? Not trees, I am talking about general graph. Let us not talk about anything special until I mention. So please, let us stick to. So now, what is a known algorithm to find diameter of a graph? Component?
whatever the exponent of the matrix.
N to the power omega, right? Fine. I think you can compute diameter in much shorter time actually. Is it possible to compute diameter of a graph in order n square time? There is no weight. Forget about weights, there is absolutely no weights, just unweighted graph. I have not written any weights. Okay. So it is indeed possible to compute order n square time, okay, for you to figure it out, okay. And these are very basic set of problems in polynomial time, right. If you do dynamic programming, then you see this problem quite often. This and this is the what we give as a basic example of this, and this we ask people in every interview. All pair shortest path we teach you, and diameter we teach you in first course in algorithms, right. And these are the algorithms, these are the running time which we provide you. Now, okay, let us get back to the threesome. How much is the running time of this algorithm? Like, do you know an algorithm for threesome which runs in order n square time, Diksha? Okay, let us hear your n square log n algorithm. Choose two numbers. Okay. Okay. Yes, fine. Okay. Yeah, so why this algorithm is n square log n? Okay. Okay, so I sort it first. Now what I do? So should I multiply here? Okay, fine. Okay, and now? Okay. 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 Okay, but that takes n square log n time. Is that correct, Ashwin? Right? I do this, I sort it, and then I look for a number, and I can do binary search. So it takes n choose 2 log n. Okay, great. Right? And but I said that we can do it in order n square time. So do we need some magic algorithm to do it in square time? Think about it. Okay. Okay. But the best known algorithm for this actually is, okay, is given by what is his name? Let me write. Baran. So there is an algorithm by Baran, Demain, and Patrasco. And the algorithm's running time is actually quite cute. It's n squared divided by log n by log n whole square. Okay. So for me, so these are the very good known algorithms. And when I say And we have not been able to get anything non-trivial for these things, except these are very highly non-trivial algorithm. But all they do is they are saving of some polylog or something in the base, right? But suppose if I ask you a very simple question, does longest path has an algorithm of running time 1.99? First of all, you must understand that this running time is not this. This n square divided by polylog n is not n to the power 1.9, it is much larger. Similarly, for edit distance, if I am interested in a running time 999, okay, still it is not, okay. For 3 sum, I am interested in say another 9, still it is not, right. And for all pair shortest path, we have an n cube algorithm, and what I would be interested in? I would be interested in something like say n to the power 2.98765, something, I do not care, okay. Same with diameter, right, same with diameter, say 1.99. Basically, this is what I am called. So, if we are able to get such an algorithm, this is what I mean by breakthrough, okay. So, for all this problem, they have a natural barrier of n square, and when we want to break over that natural barrier, or in other words, so what I say, there exists some epsilon greater than 0 such that I can do LCS in time or edit distance in time n to the power epsilon, okay. Or I can do 3 sum in n to the power 2 minus epsilon, or I can do diameter in n to the power 2 minus epsilon, or I can do, for example, here a all pair shortest path in n to the power 3 minus epsilon, right. Then I am going to call, this is my surprisingly fast algorithm for my favorite problem will be, right. Now these are the problems in P, right. So all I have written you all up until now is problems in P, okay. But there are problems beyond P for which also, if we get some faster algorithm, we would view that as a surprisingly fast algorithm for that problem. Now let me quantify some of such problems, okay. So remember this, we are like, this is just for you to explain what do we mean when we say surprisingly fast algorithm. Like I am just talking about breaking the barrier even just little bit, right. Like for any fixed constant, give me this, okay. For example, for long time, so diameter can be done in n square time, but we did not know how to do diameter even on planar graph better than n square time, and it was open problem for last 14-15 years or 20 years, I do not know for how long, whether diameter can be done better than n square on planar graph. This year in Soda, we had an algorithm for diameter which beat n squared, I do not remember what the running time is, and that is the best Soda paper for 2017, okay. So I mean these things could change, it is like they are not very, I mean they are good questions, but at least on some special instances or special classes, also if the same bounds holds, either we prove whatever we will mean to prove that such things would not happen, or we are not able to prove, and when we are not able to prove, what does it mean that we are not able to prove something, right. So there are so when you are an algorithmist, there is just one viewpoint of I have a problem and I am looking for an algorithm of certain kind, certain form, and what am I trying to achieve? So I am trying to make this algorithm and I start hitting a barriers, I am not able to do it. Now what I do, what then the next step as an algorithmist is, what is this family of instances on which I am facing this difficulty? I try to capture those family of instances, and that family of instances is either I find a strategy to break through this family of instances, great, or many cases we are able to use this family of instances to derive a hardness result, right? Hey, because look, any problem, not on every instance the problem is hard. There is an infinite family of instances on which the problem is hard. That's what it means, right? For a particular problem, I have seen a lot of people making this mistake. Then they say the problem is hard on this instance. No problem is hard on a particular instance. Problem is hard on a family of instances, right? So you never say that this problem is hard on some particular instance. No, it is hard on a family of instances, right? It's hard on planar graphs, right? But there could be, but tree also is a planar graph, right? A single vertex is also a planar graph. A path is also a planar graph. And on this, maybe we are able to solve the problem in polynomial time. But when, what does it mean? That if I give you if I give you in some instance of this class, you will not be able to solve it. And that's what it means, okay? So as I told you, so for these kind of polynomial time problem, this is what I will mean when I say something is surprising. For example, I can define this problem, there is also a notion of k sum, right? For any fixed k, does there exist k of them that sums to 0, and what is a known thing for this is k minus 1 algorithm, right? So now for k sum, what will be our surprising thing? K minus 1 minus epsilon, right? So this is what I will mean by surprising. So different problem will have what it means to be surprising differently, okay? Okay, so now I'm going to go back and look at problems somewhere else, because I need to build the assumptions, hypothesis. Okay, so now let me introduce, okay, so now I'm going to tell you problems here. So let's look at a problem called 3-SAT. What is 3-SAT? 3-SAT is basically, what is an input to 3-SAT? So here is my 3-SAT problem. What is an input? Input is a formula phi on n variables and m clauses, okay? Let's not call it 3-SAT, let's call it L-SAT, and we'll substitute L equal to 2, 3, 2. And n variables and m clauses. And how are the clauses? So each clause is basically its OR of L literal. So for example, it could be some x1 or x2 or x3 bar or x4 bar dot 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 or xl. So basically you have L literals, these are called literals, right? Xi is a variable, but xi can occur as positively, means xi, or it can occur negatively, xi bar, and all this union. So basically xi and xi bar, I in n, this is basically called literals, both in positive form as well as in negative form. This is called literal, okay? So what is a phi? So phi is basically some, it is an m clauses where each clause is OR of these variables. Now, and what is your objective? What is your objective? Objective is to find objective is to find say assignment from V to 0 1. What is V? Is set of variables, okay, on n variables, say V, okay. So basically what you are doing, you are assigning variables either 0 or 1, right. So what does it mean? If I set xi equal to 1, it means I set xi equal to 1. If I set xi equal to 0, it means xi bar is 1, right. So now look at each clause, right, and a clause is satisfied if any of them is set to 1, right. So either when this clause C will be satisfied if x1 is satisfied, or is set to 1, or x2 is set to 1, or x3 is set to 0, it means x3 bar is set to 1, x4 is set to 0, so x4 bar is set to 1, and so on and so forth, right. And the formula is satisfiable if you look at V and look at I check whether with this, if with this assignment all the clauses are satisfied, that is why it is AND, right. So a formula is satisfiable when individually each of them should be satisfiable, right, and to satisfy individually each of them any one literal could be satisfied or could be set to true, okay. Any question? Any question? Fine. So we know what the objective is to find C such that is satisfiable, okay. Okay. Now whatever little knowledge you all have, you know that 3 sat is not polynomial time solvable. So what will be amazing surprising if we get a poly in an algorithm. So this is an amazing surprising algorithm, because what it will imply? P equal to NP, amazing, right? But try to make a formula, try to make an assignment, try to have an, what do you call, try to have design an algorithm for this problem, okay, which say runs in time 2 to the power big O of n divided by log star n. This is what I want to design. What I want to design? N divided by log star n. You know what log star n is? It's like iterative logs such that from number of times you have to apply log so that n becomes some 1 or something, okay. I'm happy with this. So even if you give me such an algorithm, I'm very happy with for 3 sat. All we know with our knowledge at this point of time, the 3 sat can be solved in something like say 1.3 something to the power n, right. Of course there is a simple algorithm for this problem, which is you look at all possible assignments. How many assignments are there? 2 power n. You try each possible assignment. If any of them satisfies your formula, then you have. So basically 2 power n is the trivial algorithm or is the brute force algorithm. We'll use the word brute force, and this is a much better algorithm because I cannot hope to get to 1 anyway, right, because 1 power n is 1 power n, right. So I think this is 1.30 something, I do not remember what the best running time for 3 sat is, right, and the goal here is to minimize this base as much as possible. But this, the form of this algorithm is very different than the form of this algorithm, right. This algorithm is, if there is an algorithm with this running time, then it is going way much far more slower function than this one, right. So basically what I want to say is that I will be surprised if I have an algorithm with running time lit O of n. And what is a lit O of n? All of you know, it's basically some function f of n is in lit O of n if, what happens? If fn divided by n as limit n tends to infinity, fn tends to 0. Is this correct, right? Right? N tends to is correct, right? Okay, fine. So this is what it means, right? So if you look at your function n log star n, yes, it goes, right, as n tends to infinity, this is n will go cancel. All you are saying that 1 by log star n goes to 0. So as n goes to infinity, this will go to 0. Fine. right? So this is a completely surprising algorithm for us. But amazingly surprising is poly n. Okay. Now I can have more such problems. Okay. 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 So let's add more columns here. Super surprising, amazing surprising, super surprising, and surprising. Okay. Now let's go SAT. I do not have any. I do not have any. What do you call? Restriction on the length of the clauses. It could be anything, right? So when I say LSAT, every clause had the length bounded by L. 3 SAT, every clause length is bounded by 3, right? 15 SAT means every clause is bounded by 15. Okay, but when I say SAT, I have no restriction. Again, if I have a poly n algorithm, P equal to NP, amazing. I mean, even amazing, right? I'm very happy. But I'm going to call it, it's again a surprising algorithm, even if you come up with 1.999 to the power n algorithm, right? Or whether it is a SAT or 3 SAT, this algorithm remains the same, right? This algorithm remains the same. Whatever may be the formula is, I can enumerate all assignment and check whether my formula is satisfiable or not, right? So this is again super surprising to me, right? So, okay, so this is SAT, 3 SAT. I can define 3 coloring, poly n to the power little of n. There I don't go because 3 coloring. Do you know an algorithm for 3 coloring which is better than 2 power n? Any algorithm which is better than 3 power n for 3 coloring? Okay, let's see if we are smart enough to find an algorithm. Okay, is 2 coloring in polynomial time? Why? Great. So if I have a 3 coloring, it means it is a partition into, it's a partition into 3. So by pigeonhole principle, at least one of the sets, either V1 is less than equal to n by 3, or V2 is less than equal to n by 3, or V3 is less than equal to n by 3. Is that correct? If there are graph has n vertices, is this correct? Right? So what I do, I guess the smallest size set. I guess the smallest size set. Okay. So for example, without loss of generality, suppose this is true. Okay. Then what do? I guess V1. Okay. So what is n choose? I guess. I know the size is upper bounded by 1 to n by 3. I guess n choose n by 3. I check whether this is an independent set or not, right? Okay, right? So basically, what is my algorithm? My algorithm is guess a subset V1 of size at most n by 3, and what should be the second thing? Check whether V1 is independent. Third, check whether G minus V1 is bipartite. I'm done, right? So basically, the running time of the algorithm which dominates is the guessing of this subset, which is like n choose n by 3 upper bounded by n choose n by 3, and this is better than 2 power n. If you know binomial coefficients, it only picks here, which is basically 2 power n some root n or something. But any other alpha n, where alpha n is some constant, it is always better than 2 power n. It's like some 1.89, and this number is, I think, 1.89 to the power n. I mean, there are much faster algorithms. So of course I cannot. I mean, we know there are faster algorithms. So getting 1.99 to the power n is not a surprising algorithm for this problem because we know such algorithms exist. Okay, fine. Okay, vertex cover. Okay, now in the parameterized setting, what are we given? We are given gk, and we are looking for, does G has a vertex cover of size at most k, right? Again, poly n is an amazing surprise, but what is super surprising could also be if I have 2 to the power little of k algorithm. We all know an algorithm, if you have done a course in parameterized complexity, which runs in time some 1 point some 3 something to the power k, but the best known algorithm for vertex cover is actually 1.27 something, but that is not the point. We do not know how to get an algorithm with running time to the power little of k, and that is important, right. So with all our techniques currently in hand, we do not know to do any of these things, right. Okay. Now let me introduce a different notion of surprising, okay, a different notion of surprising which we will use and prove. Okay. So this is something which is lately has caught people's attention. Okay, imagine yourself that you are given, so let us take an example of satisfiability, SAT. Okay, what is an instance? So I give you a phi in variables and m clauses. How many clauses can it have? We don't know any bound. M could be as bad as 2 power n because it's just SAT. If I had LSAT, how many clauses it can have? Suppose the clauses are, there's no repeated clause because then they have no purposes, you can delete them. You could have as bad as n to the power L. Okay, as many clauses, M could be as bad as n to the power L. So what is your goal? Your goal is to take how much time? Polynomial time. Okay, your goal is to take polynomial time and output another formula phi prime. Okay, phi prime with the property what? What is the property? Phi is satisfiable if and only if phi prime is satisfiable, right? So in polynomial time I have got something which is phi prime, but I have not changed the answer. If I started with a satisfiable formula, I still have a satisfiable formula. If I started with an unsatisfiable formula, I still have an unsatisfiable formula. But what do I want? Size of phi prime, which is say n prime plus m prime, variables plus clauses here. This should be bounded by, okay, some polynomial n m. Okay. If I am able to obtain such a polynomial time algorithm, look, what is this algorithm? I take an instance of satisfiable formula, take an instance of SAT. I am an algorithm, I take an instance of SAT and output you an instance. I am not solving the problem. Look, I am not solving the answer. All I am doing is I am telling you, I am compressing the input and giving to you, right. I take time polynomial in the input, like polynomial in, when say polynomial n plus m big O of 1, like 10 to the power 10 is also big O of 1. I take this much amount of time and I return you something which is polynomial in n, say less than n to the power 1000 to the power 1000. This is fine for me. Choose anything, it does not matter. This is what, right? So if for SAT I'm able to find such a polynomial time algorithm, I'm going to call it, oh, this is a surprising algorithm for my problem. Fast or whatever it means, it's a surprising algorithm for my problem. For LSAT, I want the same thing, but now I tell you what I want. For LSAT, I take phi, I get phi prime, but now objective is the same. But all I want is that the size of phi prime is at most, say, n to the power L minus 1. Or say, I am happy with L minus epsilon for any epsilon greater than 0. So, right, I want an algorithm which, what does it does? It outputs me a formula phi prime, does not solve it, and it is, but what is its size? Is at most n to the power L minus epsilon. For me, this is a surprising object to have, right. This polynomial time algorithm which takes an instance of phi and returns phi prime with this much size, it is a surprising. I use the word polytime. L is a fixed constant. So, for our purposes, for understanding, let us call it 3 sat. Okay. So, what this will be? 3 minus epsilon. Okay. Just so that we know what we are talking about concretely. No L is 3 sat. What is happening? Right. But you can ask more fundamental question. Yeah, I want this, right? I can solve this 3 sat in whatever 1.3 to the power n time. So, if I give him that much time, it is definitely able to give me solve it. So, it can return, it solves it, and if it is satisfiable, it makes a trivial satisfiable instance and returns you true. If it is unsatisfiable, it makes a one clause not like x or x or something. I mean, you just give it an unsatisfiable like constant length unsatisfiable formula, return it. So, giving it a polynomial time, I find it amazingly surprising. I give it an exponential amount of time, it is trivial. But what happens if I give you 2 to the power little of n time? I said no, you cannot take this much. You can take sub exponential time. What you can do? You can take sub exponential amount of time. Then can we do this? Okay. Well, we will worry about this later. Okay. Answer to the question is yes, but in a slightly non-trivial manner, and we will need to use that at some point of time. Okay. So, this is what I mean by surprising, right. So, I have explained to you in this course what will we mean when we say we have a surprisingly fast algorithm or we have a surprising algorithm for a problem. This is what we will mean. Okay. So, this box is ticked for you people. Okay. Now, let us try to understand what do we mean by unexpected breakthrough in TCS. Now, all of you said just now, hey, if you have a Poly-N algorithm, then it is an unexpected breakthrough in, because what does it imply? P is equal to NP. There is also some meaning when it implies this, there is also some meaning when it implies this. So, for this course, to start with, here are my basic assumptions which we are going to assume, right, and let us see how the world goes after that. Okay. So, okay. So, now I am going to rub here. Okay. So, let us not call it or statements. First, 3 sat does not have polynomial time algorithm. Second, 3 sat does not have 2 to the power little of n time algorithm. And third, sat, not 3 sat, does not have 2 minus epsilon to the power n algorithm for any epsilon greater than 0. These are my assumptions. Okay. So, as I told you, right, what is this? This is basically saying this is P versus NP thing, right. So, whenever you say, if I am going to assume 3 SAT does not have polynomial time algorithm, what I am assuming? P is not equal to NP. 3 SAT does not have polynomial time algorithm, what I am assuming? P is not equal to NP. 3 SAT does not have to the power little of n time algorithm. This is what is called exponential time hypothesis. This is what is called exponential time hypothesis. Okay. So, basically if you notice, this is the most weakest conjecture. When I say weakest conjecture, something which is much more likely to happen. Strongest means we have put so, which is much more likely to fail, right. It is much more likely that P is not equal to NP than not admitting to the power little of n time algorithm. So, this is a weakest conjecture, right. This is slightly more weaker, right, or slightly more stronger compared to this, and this is even more stronger conjecture. What are we saying? The 2 power n, like try all brute force, is the best you can hope for, and this is called strong exponential time hypothesis. Strong exponential time hypothesis is actually not phrased like this, but for all practical purposes this is good enough. Okay, but I will state how it should be stated in the right way. Okay, this is called strong exponential time hypothesis, ETH, and this is called SET, or strong exponential time hypothesis. Okay, but actually let me state for all of you what actually means strong exponential, how it is actually defined. This is an implication of that, it is not the other way around. Okay, so let me okay. So, how is strong exponential time hypothesis actually defined is the following. Okay. So, actually SET is defined this is why I define. Okay, there is no epsilon greater than 0, okay, such that for all k, let us say L strictly greater than or equal to 2, LSAT can be solved in time 2 minus epsilon to the power, right. What is, there is no epsilon greater than 0 such that for all L greater than 2. So, I cannot find an universal epsilon such that 3 SAT, 4 SAT, 5 SAT, 6 SAT, 7 SAT, any SAT can be solved in time this. Clearly that implies this, that assumption implies this, because if you had such an object, then clearly I have such an algorithm, because any SAT instance is some LSAT algorithm, I will apply that algorithm and it is a universal epsilon. Okay. Now, one thing which I did not tell to people who are working in parameterized complexity, for us surprising thing could also be, which I forgot to tell you, is in FPT sense what more surprising thing. So, when you write lecture note, just please add it up, add it back. Okay, okay. So, is independent set. What is independent set problem? Input is G comma K, question, does G has an independent set of size k, of size greater than or equal to k, dominating set input g comma k. Question: does G has a dominating set of size at most k, size at most k? And what is a surprising thing will be here? Surprising thing will be an algorithm with running time f of k. This is a surprising algorithm. We will deal with this in the next 2-3 lectures in the normal PC course, right? I will give some reductions. Okay. Now, so this is what for now. For now, suppose these are my surprises, right? These are my unexpected breakthroughs in thesis. If this is what I assume unexpected breakthrough in thesis, then what kind of theorems do I like to prove? So the kind of theorems I would like to prove is the following. Okay, so let's state this theorem for edit distance and longest common sequence. Longest common sequence, what is this? If for some epsilon greater than 0, if for some epsilon greater than 0, we can solve edit distance or longest common subsequence in time n to the power, no, we cannot say big O here, 2 minus epsilon, then we can solve LSAT in time two minus d to the power n for some d greater than or equal to 0 and for all L greater than 0. It does not matter because 1 and 2 anyway we can solve in polytime. This is what I would like to prove, right. If for some epsilon greater than 0 we can solve our problem in this much, then we can solve LSAT in this much time, right. Okay. Now let us try to understand, decipher. So what is it actually is trying to tell us? So let us try to understand what it means. Right. So let us draw a box. Okay. What is this? Faster LCS or edit distance implies what? Faster LSAT implies what? That set is false. Implies and what is faster here will mean. So just to have a different variables, let us call will denote capital N for number of vertices or say length of the string, okay, and N to denote number of variables, okay, for now, okay. So what does this imply? Implies maybe algorithm for LSAT, and then that implies the set is false, right. Now right. What? No, it's not if and only if. And I don't think, I mean that will be a miraculous, okay, okay. but or I mean we need hard work to show if and only if. Okay. Okay. So what about what does it implies? Okay. Okay. So let's see. You understand this. Let's see. And faster longest common sequence edit distance implies faster algorithm for 3 SAT. It implies something. Okay. Now let's see what we put here and what we put here and what does it imply, right? So for example, right, so in the same setting if we put this, then we got this. So for example, if I had put 1.99, that's my still faster for 3 SAT, say n to the power 100 algorithm, what will it imply? If I can give a reduction such that if I had a faster algorithm for this, then it implies an algorithm of running time n to the power 100 for 3 SAT. Then what does this imply? Yes, then it implies right, then this implies Seth is false. This implies P equal to NP, right. So like whatever we are able to assume will contradict different assumptions, right. That is why we have different set of assumptions, because we are looking for a different form of running time, and based on different form of running time we will be saying, oh, this is not possible, that is not possible, and that is the whole goal. For example, if I had said here same thing, and here I said, oh, this implies 2 to the power, okay, so let's keep it same, but here I say n divided by say log n algorithm. What will this imply? If I have this, then this imply an algorithm for 3 SAT which run into the power big of n log n. What does it imply? What fails? What? ETH fails, right. So now there are different ways of like starting from where do we start, what we end up designing, we end up contradicting, right. So they all are interrelated, they all are closely related to each other. So now we have to okay. So now I would like to understand what does this means, right, what does it mean to have such kind of things, okay. So now, so these are the kind of statements we would like to prove. Those are our assumptions. What are our assumptions? For now we will have more assumption as we go further, okay. But for now let's stick to these 3 assumptions. 3 SAT cannot be done in polynomial time, that's P not equal to NP. 3 SAT cannot be done in 2 to the power little of n time, it is your ETH. SAT, not 3 SAT, cannot be done in 2 minus epsilon to the power n, that is your Seth. Or in alternatively, for every, like there is no universal epsilon such that every L SAT for all L can be solved in time 2 minus epsilon to the power n. That's all. There is no universal epsilon which can solve this, right. So these are my 3 assumptions. It is nothing about anything else, right. So when you say P is not equal to NP, all you are doing, you are assuming that SAT cannot be solved in polynomial time, right. When I assume, I do my normal usual reductions and everything, but all I do when I 3 SAT, that I assume that such an object is not possible. When I do this, I say such an object is not possible, right, that's all. But now I want to go through all the 3 reduction, okay, all the 3 reduction, okay, and I want to say what does it implies, okay, what powers do we have, okay. Okay, first of all tell me, so let's look at it doesn't matter which problem we pick up, okay. So for sake of brevity or for sake of understanding, let's fix our problem to be longest common 6 here. This is the problem which I fix myself to be. And I want to get the first kind of reduction, okay? Or forget about faster LSAT. For now, let's just keep SAT. Like this is what we want to do. Okay, so there are a lot of things which we have to keep into control.
But we know that there is, say, a faster algorithm for LCS, I mean, in little o of n square. Does it have any impact on LSAT or anything?
We'll get there, right? That is exactly what the point is. I mean, it depends on what you are able to achieve, right? So for now, let's just, I will come back to your question. Remember this question. It's a very nice question. And what implication it could have, right? Because in circuit stats or in the complexity theory world, now what does Ryan-Williams algorithm tells? Well, for some family of circuits, right, if we can design an algorithm which is 2 power n divided by some poly n, like slightly super growing function, even that fast algorithm would imply certain collapse in circuit complexity, right? So in that sense, this is what it is, from 2 power n divided by poly n is no, like it's just minute improvement, right? In terms of world, this is a minute improvement, but it could still imply circuit complexity lower bound. So it depends on how tight your objects are when you are trying to do something in between, right? How much you allow yourself to do something, okay? So it depends completely on how tight things are, and I will quantify what do I mean by tight things are in a minute, okay? And then you will understand whether it can imply or it cannot imply, and if it can imply, what you need to do that it can imply this, okay? Fine. So suppose here, what am I allowed to do, right? Some things we must understand, okay? So what does it mean? So I have a faster algorithm, this is my assumption, right? Then I can do this. This is basically what we are saying, right? So now, what should be, what does it mean to say that if I have a faster algorithm for this, then I can solve this? What does it mean? What does it mean when I say, what does this implication mean? What should be doing? Right? All we have is in this. So, right, what should you do? Right. So we have a black box. Okay. So we have a black box. What is this? Faster LCS. Let's fix a form of running time. Let's not worry about the constants hidden because those can be taken care. Suppose it is 1.99. This is what all we know is that this algorithm runs in time n to the power. So if I give him two strings of length exactly equal to capital N, it will output me the longest common subsequence between them in running time n to the power 1.99. This is guaranteed, right? Now what I want, this is what my black box is, right? Now I want to solve SAT. So this is what you should always remember, what is given and what is not given, right? Otherwise half the people have a trouble, oh, they show the reduction other way around, okay? So no, this is what black box I have, right? So now look, I have an instance of SAT, I want to solve it faster. So I should give him to this guy, right? So now I should take an instance of SAT and create instance of him, right? Okay, fine. So what is an instance of SAT? So instance of SAT is some phi, n variables and m clauses, okay? What do I need to produce? What do I need to produce? I need to produce x comma y of LCS, okay? I need to produce, okay. There is something called production time, right? I am allowed to do this, right? Before I give him. Now you ask several questions. How much am I allowed to do? How much am I allowed to use. Yeah, like look, if I'm going to make xy, right, for example, if I was ruling out, I mean it doesn't matter whether we do 3 sat or sat, does not matter, okay, but we'll stick to this. If we were ruling out this, if we were ruling out this, then we will have to worry about a little. If we are ruling out this, we will have to worry about this little. But how much time do you think I can allow myself to say something here? How much time can I have? Can I give myself?
2 minus epsilon power n to reduce that.
No, I have told you. I'm trying to rule out, say 1.99 to the power n. This is what I want to rule out. I'm not trying to rule out 2 minus epsilon.
So that much time you can take for this reduction, and also how the capital N that also.
Wait. So look, this is where the magic comes. So when I start assuming stronger assumption, right, some things becomes much more harder, but something becomes easier, right. I can take time. Why? So what will be the running time of the whole, because we will have to capture, right, I have to solve, right, and then it outputs me longest common subsequence, longest common subsequence of xy, and based on that I look at this longest common subsequence. Based on that, what I have to decide? Need to decide whether phi is satisfiable or not, right. So this is the whole thing, right. So when I say the faster algorithm for SAT, it means I get an instance, I create an instance for this, I run this algorithm and this, and whatever it is, so length of x is length of y, and what is this? Whatever that means, and we need to fix this. And this algorithm runs in time n.19 and run this, and then maybe in polynomial time, or I'll look. So what is the total running time of this algorithm? First is production time, let's call it PT. Okay, so the total running time is going to be production time plus time taken by the black box, time taken by the black box, plus what do you call inferring an answer by looking at the output, right, that also is the amount of time it takes, right, okay, inferring answer from output. Now let's try to understand that. How much can we allow n to be? Because after all this is addition, so they are like part of big O, so we don't care much, right, they are like part of big O. So what can be the size of n be? Calm down, Dipto, please. What do you think I can allow n to be? What do I want to contradict? If using this I want to say I cannot have 1.99 to the power n algorithm, so maybe first of all, if that is the running time which we want to say, maybe we should just make it 8 here, or maybe we should say, okay, I will allow you epsilon n for any epsilon greater than 0. Okay, this is allowed, this is fine, you take less time, fine, it's okay, fine, this much is allowed, so you take a little bit of time, okay. But what can be the size of this?
Should be 1.999 minus epsilon to the n by 1 by 9.
It's very trivial actually, okay. What is very trivial? I mean this is not something which is that magical that you people have to worry about it, okay. So what is this? So I do a very simple maths computation. What is this? What do I want? I want n.199 to be less than equal to what? 99 minus epsilon to the power n. This is what I want. I can solve this, right? Right? Whatever that n comes, I can fix that. All I want is this should be less than or equal to this. That's all, right? Now, if you notice how large x can be, if you think a little bit, it is like roughly like it can be as bad as slightly bit smaller than 2 to the power n over 2. My x can be as bad as 2 to the power n over 2. For example, if x had, how amazing, if x had 2 to the power n by 4, then what is this? This is like 2 to the power n by 2 at best, which is much smaller than 1.99 minus epsilon to the power n I have allowed myself to be, right? So there are few things which you have to worry about: time, right? Size of the input we feed. And how do we capture this? We just solve the proper recurrence, right? Solve the recurrence, right? And how do you get this? Solve the desired recurrence. Right? And what is the production time? Whichever world you live in, you just go slightly lower. That's it. Right? Okay. And here also I need to infer this in 1.99 minus epsilon to the power n, and then say, hey, we cannot have such an algorithm, right? But imagine yourself, I start, so this is the first format of the reduction, right? How much am I allowed to use? But now let's just go back. Let's go back and let's start let's look at this. What am I allowed to use? Okay, fine. So I'll say, okay, fine. I have 3 sat, and I assume that it has a polynomial n to the power 100 algorithm, right? So how much am I allowed to use here? N to the power 100 minus epsilon, maybe. In fact, who cares, right? Now you look, when you say poly log n and everything, this is where the tightness starts coming in. So you have a different objects to fix tightness, right? And what result you are going to get is based on what assumption you make, the size, how much time it takes to produce the instance, and what are the size of the instances, and how much time you are going to take infer. So for example, I can allow log star n. This is fine. Why? I mean, this is better than n to the power, like this is strictly less than n to the power 100, right? So I'm perfectly fine. I'm perfectly legitimate even allowing as much running time as log star n, right? That's okay. I cannot allow, I mean, I want to be slightly worse, like slightly better than n to the power 100, and by dividing by log star n, it is almost n to the power 100, slightly worse. That's okay, fine, right? So basically, or think of this way, it is n to the power 99 times little of n. That's all that it is. This much I am allowed to use. Now you can use whatever little of n you are happy with, but it should be little of n, it cannot be n, because otherwise we will not be ruling out whatever we are interested in. And then I can eat, this is why we have a constant, because whatever constant you want to find, the big O will take care of it, but even with that constant, it is never going to be more than n to the power 100, fine. Now, what should be x and y? Well, I go back, but now I solve different recurrence. What will I solve by solving it? Okay, so for example, forget little o of n, then I would be solving, well, this should be less than or equal to n to the power 99. So what is n? Well, this implies that n should be less than or equal to n divided by 99 divided by 1.99. That's all that it says, right? Just take 1 over this both sides, right? Take power of 1 over this both sides. This is what you will get, right? So this bounds us that n should be less than or equal to how much? 1.99, right? Okay, so your instance of xy should have size exactly equal to this much. Okay, fine, then you produce this because of your selection of n. This is great, this is strictly greater than n to the power 99 actually. So this is n to the power 99, which is great. So this is like, here we took this So think n to the power 99 we took, this is also we took n to the power 99, great, and now I should be able to infer my answer by looking at this, that is perfectly fine. But that also I am allowed as much as n to the power 99, fine, right. So the total running time is n to the power 99 and I am happy, right. So if you notice, different reduction allows you different leeway, right. For example, now let us look at this one, right, okay, fine. Now what I am allowed to use? I am allowed to use, well, third one, say log square n, right, it is okay, it is better than log n by log n, right. Now in fact I am allowed to use anything log 1 plus epsilon n. Now when you say if they have this sub exponential algorithm, will it rule out something? Yes, then you have to go and look at what these parameters are, tighten them up, right. What is the right constants you want, and then you have to like go through everywhere so that you can make your maths go through. This is what it means when you say, can I rule out this? Yes, you can, but then you have to do the maths completely, properly, clearly, and do this. So this much is allowed. Now how much is this allowed? Well, I do nothing, I just go and solve this. I solve this equation, which is okay, fine, 2 to the power n divided by log 1 plus epsilon n. So what is n? This implies n to be whole power 1 by 1.99. So this will become basically less than equal to 2 to the power n divided by 1 plus epsilon log n to the power 1 divided by 1.99. This is what it is. Lower bound for what? No. Why? Why do I need lower bound?
Because I want to see that it is 1.99 and in power 1. I have an algorithm for LCS which is in power 1.99 but not in power 2.
So where do I need lower bound for?
If instead the LCS algorithm that I would have been using was in power 2 in fact.
No, it is using n to the power 1.99.
Yes.
Okay.
Now this is the time we are fixing. For this part we need this much time.
No, I am allowing how much time is allowed. I am not fixing anything.
Yes.
If I fix this, what automatically most things gets fixed and based on your assumption. That is all that I am trying to say. What I am trying to rule out under which assumption allows me certain leeway, certain freedom.
For all of this, all three of these cases, what I'm asking is that if this faster LCS algorithm
Yeah.
not in power 1.99, but I don't have a faster LCS algorithm, the algorithm that I have is n power 2.
Yes.
Is n squaring.
Okay.
Now
then I don't rule out anything.
Then this n becomes less than equals to 2 power that divided by 2.
Yes.
That is less than this.
Less than what?
What I have.
Yeah, but then I already have spent, look, I wanted to say that I cannot have an algorithm with this much running time. I already have spent that much time computing this. So how do I rule out this algorithm? Imagine yourself that I had n square algorithm here and the instance I fed is 2 power n by 2, right? Then I get 2 power n already here. If I had n square algorithm and I fed him, all I am saying that xy is less than equal to 2 power n by 2, right, or 2 power n by 2 something. But if I fed him that, it will give me something. But that does not mean that I am able to rule out my algorithm, right?
What is the total time that I'm taking?
This also takes certain amount of time, right? This also takes certain amount of time, right, when I run this. So if I feed him an input of 2 power n by 2 size, it's not n. So n is like hues, and that is what you exploit. Imagine yourself that, think of about yourself that just for a moment think, I'm trying to give a reduction from an instance, from a problem which is so called NP hard to a problem which is polynomial time solvable, right, which is polynomial time solvable. Okay. So there's two things could happen. Either I feed him a polynomial size instance, but I have spent lot of time finding such a small guy, right, that could happen. But imagine yourself, is it possible that I also produce a small instance, I also take a small amount of time here? That's not possible, because then I would be making a polynomial time algorithm, right, by giving a reduction from a NP hard problem, making it an instance of a polynomial time problem, right, and do it. So such kind of reduction we shouldn't even hope for. No. Why n has to be bigger than some value? Imagine yourself, this is exactly where the problem lies, right? You are looking at each instance. Imagine yourself, if my assumption is really hard, if my assumption is really correct, there will be some instance for which it will be tight. Do I need to care about it? Instance is not hard, family is hard. No, this is important aspect to understand that. What you are talking about, each instance it means on each instance I should force him to take some amount of time. If I am giving a lower bound on each n, for every input if I am giving a lower bound on this, then I am forcing on each instance my algorithm takes certain amount of time. Is it humanly possible? Then does it happen ever? Right? So I don't need lower bound on the size, I just need an upper bound so that I can guarantee that on every instance of SAT the algorithm does not supersede, right. But the point is, if my assumption is hard, there will be instances where it will be tight and I don't have to worry about it. Like for example, polynomial time algorithm, right, we don't know, right. I mean there are instances for which it will take n to the power 100, n to the power 10,000, we do not have any idea. Okay. So what will we do? After the lunch at 2 o'clock, we will carry on our discussion and then we will start getting into some concrete reductions. But before that we have to build, what do we mean when we say, okay, we are going to show this, like it should be very clear in our head what we are trying to show, right. So if I say n cube, what it should mean here, right, and we will see those kind of things after the break. So say we meet here at 2, okay.